Okay, so you might be asking, what's that all about? Well, if you've ever been in my class, you realize that sometimes things get pretty serious, and sometimes they're not so serious. Well, this is Miley's series. She's not so serious. And this is Billy right now. Look, check that mullet out. That is a series mullet. You have to go all the way to Dayton, Ohio to get a mullet that long. So that's what we're talking about today. Sequences, how to be series, and summation. Let's figure out what this means. So we get 14.1 sequences, series, and summations. We got x cubed. This is a great lesson because you know why? Well, just because I'm really serious in this lesson. Let's look at the following list of numbers. They're called sequences. Now, sequence is just a list. If you notice here, we have a list of odd numbers. We have a list here of fractions. These lists are called sequences. So if you ever hear about a sequence, they're just talking about a list of numbers. Now, if you want to get really precise, a sequence is a function that has integer or whole number values that you can plug into the domain, which means you get a list of numbers out as the range, blah, blah, blah. Good enough. All we have to worry about is that it's a list of numbers. Let's see how this works. A, with a little tiny 1 down there, we say that's a sub 1. A sub 1 here is 1, and a sub 2 is 3. So that means the first term and the second term. A sub 1, a sub 2, so on and so forth. Down here at the bottom, a sub nth. That means the nth term. It's generalized. Now, in the middle, we have 13. If you want, you can count these out to 13, but there's a better way to do it. I'm going to show you the better way right now. We're going to come up with a general or explicit rule. So let's call this the explicit rule, which means that when I plug a number in, it's going to take me right to the term. I don't have to worry about it. So if I want the 13th term, I'm going to plug a 13 in, and it's going to take me right there. So we first have to look for patterns in our sequence. So what are the patterns here? I notice that it's going up by 2, up by 2, up by 2 every time. So you add 2. Well, repeated addition is the same as multiplication. So if I just take the term number and multiply it by what I'm going up, it should get me close, right? Let's do that. Let's call this 2 times n because I'm going up by 2 every time. So when I plug a 1 in, I get 1 times 2. That's a 2. And then I plug a 2 in. I get 2 times 2, which is a 4, and then a 6, and then so on and so forth. That's close, but it's not quite right here. If you notice, we have 1, 3, 5, 7, 9. We have the odd numbers. So that first number in my sequence is 1 too high. So if I take my rule and I subtract 1, that'll give me the terms that are listed here. Let's try it out. So I plug a 1 in. 2 times 1 is 2. 2 minus 1 is 1. Plug a 2 in. We get 2 times 2 is 4. 4 minus 1 is 3. Let's try the fifth. Here's the fifth term right there. It's 9. Plug a 5 in, you get 10 minus 1 is 9. So it seems to work for all of them. So that means I can plug this 13th term in. I get 2 times 13, subtract 1, I get 25. That makes it really easy to find different terms of a sequence. Let's look at the next one. It's a little more complicated. If you notice on the top, we have 0, 1, 2, 3, 4, 5. On the bottom, 2, 3, 4, 5, 6. You know what I'm going to do? I'm going to make this pattern go backwards. I'm going to make that 0 over 1, which, of course, it reduces to 0, but it helps me see the pattern here. The first term is, let's look at it. There's a 1 in the bottom, so you know what? It's over 1. And there's a 1 less than that in the top. All right, so that's 0. We know that's 0. The second term, there's a 2 in the bottom. All right, I'm kind of getting this. There's 1 less than that in the top. Notice the numerator is always 1 less than the denominator. So that equals 1. It's just 1/2 there. Easy enough. What about 54? Can we figure that out? There would be a 54 in the bottom because the term is in the bottom, and then 1 less is in the top, so it's 53 out of 54. So for n, we would say there's always 1 less on the top, but n is in the bottom. This is called the explicit rule again. And now we're going to talk about converging or diverging. By the way, does this work? I mean, plug in the fourth term. You get 4 minus 1 is 3. All right, that seems to work. And then we have the 4 on the bottom. 1, 2, 3, 4. That's the term we're looking for. It does work. Now, if you notice, the 53 out of 54, what's that equal to? That's like 0.99, basically 0.99, right? 0.98, 0.99, somewhere in there. It's getting closer and closer to the value of 1. In fact, as we start right here, we start at 0, and we have 0.5, and we have 0.67. Notice how we started 0, but we're getting closer and closer and closer. This one here is 0.83. Okay, that term right there. And then we go all the way up to 0.99. Will it ever cross 1 or get to 1? No. As this sequence goes further and further and further away, it gets really close to 1, but it never gets to 1. But we say it converges to 1. It gets closer and closer to 1 here. So we're going to write that down. It converges to 1. Let's look at our other one. Our other sequence here, 1, 3, 5, 7. It's always going up by 2. Is there some value it gets closer and closer and closer to? No, so we say it diverges. It just goes higher and higher. So some of you are thinking, yeah, it gets closer to infinity. No, that's not one value. Okay, so if it gets closer and closer to one value, we say it converges. Otherwise, we say it diverges. All right, now let's look at the last example here. Could be the most easiest because they gave us the explicit rule. That makes life easy. So for the first term, we just plug a 1 in, and we get -3. For the second term, we plug a 2 in, we get a 9. Then we get a -27 for 3, and then we get a +81. So 100, we just have to plug that in, -3 to the 100. You know what? This number's so big, I'm not going to worry about it. I'm going to leave it in this form. But you know what? Can you tell if this converges or diverges? This definitely diverges because it's going up. It's oscillating here between negatives and positives, and it's getting higher and higher. Definitely does not converge. All right, so you have 3 to try by yourself. The last one is super tricky. If you get it, I'll be super proud of you. Pause the video. Go. Okay, so we have the first one all done here. Pretty easy, the first one. If you notice, a 1 goes to a 6, and then we have 8. And if you notice, the powers are getting, well, not the powers, but these terms are increasing by 2 every time. So you know it's 2n. And then if you plug a 1 in, you get 2 times 1 is 2, but you have to get a 6. So you add 4 and it seems to work. Now with that rule, the 19th term would be 38 plus 4, which is 42. Easy enough. This definitely does not converge. It's divergent. So it goes forever away, higher and higher. We're good with that one. Any questions? Good. We're going to the next one. Now the next one you notice looks a little scary. All right, you plug a 1 in. You're going to get -1 squared, which is +1. Then you get -1 to the third, which is -1. So it's 1, -1, 1, -1, 1, so on and so forth. So basically, what do we got? You can plug it in, you get to 44th. I noticed that the even numbers are negative, right? Negative, negative. They're the even numbers. The odd numbers are positive. So the 44th term should be negative. This definitely diverges because it does not get closer and closer to one value. That's what converge means. All right, last one. All right, the last one here, here's what I noticed. We start at 100, go down to 10, go down to 1, go down to 0.1. We're dividing by 10 every time. Do you notice that? This one is super tricky. So we start at 100. I'm not going to worry about the negatives yet. We'll worry about that at the end. But we start at 100, go to 10, go to 1, go to 0.1, go to 0.01, so on and so forth. So we're dividing by 10 every time. So I think of that as, if we do this, 1 over 10 to the n. All right, so when n is 1, then we'll multiply by 1/10. If n is 2, we multiply by 100. 100th, sorry. If n is 3, we multiply by 1,000th. So it gets smaller and smaller and smaller. Now, as we're working this out, what do we need that first term? That first term needs to be 100. There's 100. If we put a 1 right there, if I put a, I'll need to put 1,000 out here. Right? Let's try to figure that out. So if I put 1,000 out here and I multiply by 1/10, that's 100. For this, all right, let's put that in, -100. The second term is 10. So how can I get a 10? Well, the second term, I plug a 2 in here, I get 1 over 10 squared. That's 1,000 times 100th, or divided by 100. That's going to give me 10. Let's try the third term. Plug a 3 in, you get 1 over 1,000. It's 1,000 times 1 over 1,000. They cancel, you get a 1. So now the only other parts to worry about that negative. The first term has to be negative, so I multiply by -1. The first term, or the nth term, has to be negative. That means the second term, that would square and become positive. That seems to fit. So this is our nth rule. It is a little difficult. Now, there are other ways to do it as well. This is the way that I saw it. You can rewrite it a different way, and it can give you the same exact sequence. They could be equivalent, but this is how I'm going to write it. It's kind of ugly. So now I can plug in, I can say, all right, the ninth term is going to be 1,000 times 1 over 10 to the ninth, and then that's just going to be times -1, right? Because that's going to be the ninth power. So I can actually just make that -1,000 times 1 over 10 to the ninth. Now, let me show you one way that we can write. I'm going to do this up here. I'm going to show you how we can change this a little bit. That first term, 1,000, we can see it as 10 to the third, right? And so 10 to the third times this fraction here, which is 1 over 10 to the n. What's our rule? All right, I'm going to rewrite that as 10 to the third. Oop, can't see that barely. 10 to the third over 10 to the n. The rule is when you are dividing, the exponent rule is you subtract. So we could just call that 10 to the 3 minus n. That's a different way to do it. Then you have to put that -1 to the n on there. Get the same exact answer. It's the same exact answer, but you know what? There's no right answer because both rules will find this sequence. They're both explicit rules to find this sequence. Does it converge or diverge? Tell you what, it's getting closer and closer to 0. Even though it's oscillating between negatives and positives, that converges. So we're going to say it converges to 0. All right. Easy. Okay, that last part was crazy, especially that general rule at the end. You have 1,000 and 10 to the n and negatives and all that kind of stuff. So sometimes it's a little bit easier if we define things based off of what we saw before, the term before. That's called a recursive formula. Now, recursive formula, they're kind of easier, I think. I think they're easier, but let's see how they work. Here's the first example. Find the first 4 terms of the sequence using the recursive formula that's given. Now, recursive means you need a starting point. So a sub 1 is 2 in this. The first term is 2. Then what do? Well, here's the recursive formula. You take, to find the nth term, you take the n minus 1, a sub n minus 1. That's the term before it. So I'm just going to refer to it as the term before it. You multiply by 4 and you subtract 3. So if a sub 1 is 2, then a sub 2 is, so it'll be 4 times the term before it. So it'll be 4 times 2, and then we subtract 3. All that equals what? 8 minus 3, which is 5. Let's find the third term. Third term would be 4 times the term before it. Term before it's 5 now. So this equals 4 times 5, and then you subtract 3. That's going to equal 17. Let's find the fourth term. Fourth term equals 4 times the term before it. Term before it's 17. And then we subtract 3. I think that all equals what? We get 40 and 28, 68 minus 3, 65. All right, so the first 4 terms, that's what they're asking us to do, are 2, 5, 17, and 65. That's simple. And this is called a recursive formula. Let's try the next one, number 2. So we have a starting point of 16, and to find the next term, we take half of the term before it. Half of the term before it. So a sub 2 would be 8, because that's half of 16. A sub 3 would be 4, and a sub 4 would be 2, because I'm taking the term before it, and I'm finding half of it. It's that simple. You try the last one all by yourself. Pause the video. Go! Pause that video. All right, for the last one here, the second term, what do we get? I'm going to go over it. So the second term would be 2 times the term before it. The term before it is 1. So that would equal to 2. The third term would be, well, remember it's n times, so it's 3 times the term before it. 3 times 2, which is 6. And the fourth term here would equal 4 times the term before it. 4 times 6, which is 24. So here we get 1, 2, 6, 24. That would be that sequence. Now, a lot of times in math, we love to add these sequences together. We love adding all this stuff together. And so if we do that, it's called a series. Let me show you some series right now. Some Billy Ray series. That's pretty series. All right, so the sequence 12, 15, 18, 21. This is a sequence because it's just a list of numbers. It would have a corresponding series of 12 plus 15 plus 8. Notice what I'm doing? I'm just adding them together. That's all a series is. You just add the terms together. So to help us write this compactly, we use sigma notation. Sigma notation. And sometimes this is called summation notation. Summation. But you know what? There's too much rhymage in that summation notation. That's crazy. I'm not going to say it like that. So I call it sigma notation because this thing right here is called sigma. It's a Greek letter. And in mathematics, it represents adding all the terms together. So we have K here is called the index. Okay, that's the letter that you plug into. We have a lower bound, and we have an upper bound. Okay, the upper bound is where you stop, the lower bound is where you begin. That makes sense. And you just plug numbers in. Let me show you how it works. Oh, by the way, let's finish this long generalized thing. This just basically means that you plug a 1 in, so we get the first term plus, and then you keep going. It's the second plus, the third plus, the fourth, and you keep going plus, dot, dot, dot. That's what the dot, dot, dot means. Plus, I got one extra dot. You go all the way up to a sub n, which means you stop at the number at the top. That's why it's called the upper bound. Now we'll do some, now we'll do some examples. Yeah, now we will. Right now. All right, right here. So we start at 0. We're going to plug it in. 4 times 0. Plus. And then we keep raising it until we get to a 5. So that'd be 4 times 1, plus 4 times 2, plus 4 times 3, plus 4 times 4, plus 4 times 5. And so when I add all that together, what do we get? 0 plus 4 plus 16 plus, 16. What's going on? It's not squared. I'm just keeping you on your toes. Plus 12 plus 16 plus 20. So these two equal 20. That's 40, 56. And okay, so let's try number 4 here. So what do we get? The summation notation. This is the lower bound. We have n. We're going to be plugging into n. That's called the index again. So we plug into n. We start at 0, and we go all the way up to 5, and then we quit. So let's plug that in here. By the way, the directions here say rewrite each series as a sum, so I don't have to figure out a final answer. I just have to write it as a bunch of terms being added together. What do we call that? A series. There you go. So we're going to plug it in. So we get 4 to the 0. And then it keeps going up. So we get 4 to the 1 plus 4 times 2 plus 4 times 3. I said 4 to the 1, but that's not really what's going on. Plus 4 times 4. And then what do we get? 0 plus 4 plus 8 plus 12 plus 16. That's basically it. We're done. 1, 2, 3, 4, 5 terms. Start at 0, go to 5. Oh, that means I forgot one. Got to go up to 5 plus 20. Ta-da! That is our sum. We wrote this series as a sum. Okay, so we try number 5. Let's move this stuff. Sorry, I'm moving him. Number 5. It's p to the p. So we're going to start with p equals a 1. So we're going to plug a 1 in. So it's 1 to the first plus 2 to the second because p goes from 1 up to 2. Then it goes up to 3. 3 to the third. Then it goes up to the fourth. That's the upper bound. We stopped right there. So to write this as a sum, I'm going to figure it out. 1 plus 4 plus, what do we get there? 4 to the fourth is the same as 4 squared times 4 squared, which is 16 times 16, which I know is 256, so I'm done with that one. Done! I don't have to figure it out because it says write it as a sum. All right, you try it. Pause the video, try number 6. Go! All right, so for number 6, we get 7 times 10 plus 8 times 11 plus 9 times 12 plus Mr. Kelly runs out of room, 10 times 13. All right, so what does that equal? So we get 70 plus 88 plus 130. That is a sum, so we're done with that one. Hopefully you got that one right. Let's go on to number 7 here. Evaluate. This is different directions here. Evaluate means you got to figure it out. So here we go. So it's 3 to the n, and we're starting at 0. So we're going to have 3 to the 0 plus 3 to the 1 plus 3 to the 2, so on and so forth, until we get to the upper bound, which is 4, 3 to the 4th. So this is going to equal 1 plus 3 plus, what do we got, 9 plus 27 plus 81. We have to add these all together, though, because it says evaluate this time. So I'm going to do, let's see, 1 and 9 is 10, and then 3 and 27, that's going to give me 30. That gives me 40, 121. This all equals 121. See what I did there? Double check my math, please. If I'm not right, leave me a comment or something. All right, number 8. This is kind of tricky. We have a negative 1. You're going to see what this does, and we have a 1 over h. So I'm just going to plug it in and see what we get. So we get negative 1 to the 1 minus 1, which is 0, times 1 over 1, plus, I'm just going to leave that there for now. We're going to go to the next number, 2. So it would be negative 1 to the 2 minus 1, which is 1, times 1 over, and in this case, it would be a 2. Right? I'm going to put that in parentheses so we don't lose it. Let me put that in parentheses so we don't lose it. Plus, we have negative 1. This will be the third term, so I'm plugging a 3 in, so that's going to give me 3 minus 1 is 2, times 1/3. And lastly, we have negative 1 to the third power, 1/4. All right, so how does this all work out? We're going to evaluate, so we need to figure out a final answer. But I wanted to write this all out. It's going to come in useful later. So negative 1 to the 0 power is 1, times 1. That gives us a 1 here. Plus negative 1 to the first power. So it's not really going to be plus. This is going to be minus. This comes out to a negative 1/2. So I'm just going to write minus 1/2. Then we're going to get a positive 1/3 and a negative 1/4. See what I did there? That's why I left it all out. See, negative 1 to the third power is negative, so you get negative 1/4. If I work all of this out, look, we need common denominators, so we're looking 12ths. So 1 minus 1/2, that's a 1/2. So we basically have a 1/2 plus a 1/3 minus a 1/4. If I go into 12ths, that's 6/12 plus 4/12 minus 3/12 would equal 10 minus 3. All this equals 7/12. All right. Write all that down because I'm going to refer back to it later. Okay? Last one. You try by yourself. Pause the video. Go! Pause that video. Okay, so I plug in. I get 8 plus 25 halves plus 18 plus 49 halves. 25 halves is just 12.5. 49 halves is 24.5. I add them all together. Half and a half as a whole. Blah, blah. I get 63. All right, this brings us to our very last part. Now, I wanted to write all this out so we could see in number 8. Right? Probably could have done some of that in my head, but I wanted to see for number 10. See how that oscillates. We say that oscillates between positive and negative, positive and negative, positive and negative. Starts at 1 across the numerators all the way. And we have, I'm going to rewrite that, over 1. So we have 1, 2, 3, 4, 5, 6 on the bottom. Now what we want to do, our goal, is to rewrite this series in sigma notation. Now I'm going to do it the easy way first. I'm going to write out the sigma. That is a fancy sigma. Notice that we have, if we start with, we want to start with k equals 0 or k equals 1. I'm going to start with k equals 1 first. I'll show you why in a second. The next one will be easy if I do this one. Because the first term is going to be 1 over 1, 1 over 2, 1 over 3. So this is 1 over whatever number's in the bottom. So here it's k, so I'm going to write 1 over k. The only problem is, we have to worry about that positive, negative. The first one has to be positive. The next one has to be negative. When I sub a 2 in, we have to make this negative. So the only way we can do that is if we add this little times negative 1 on it. And I want the exponent on the negative 1 to be odd when k is 2. That is a weird way to think about it. Let's think about it when k is 1. When k is 1, this thing has to be positive. So I plug a 1 in there. With that negative 1, it's not going to be positive. So I'm going to go like this, k plus 1. Ta-da! What that's going to do is it's going to make the exponent on negative 1 positive. Because when k is 1, I plug it in, you're going to get an exponent of 2. So it's negative 1 squared. That becomes positive. That gives me my first term. I'm going to say that all again really quickly. Okay, so look at the first term there. It's 1 over 1. I notice that the denominator here is whatever the term number is. It's the same. So it goes 1, 2, 3, 4, 5, 6. That's easy. So it's 1 over k, and then I just have to worry about whether it's positive or negative. The first term has to be positive, so I write negative 1, put in parentheses. If I leave it as k to the k power, it'll end up the first one will be negative, so I want to shift it 1, so I just do a plus 1. Guess what? I could also do a minus 1. And you know what? That's what we have up here, negative 1, h minus 1. It doesn't matter. As I said, we have different notation. We have different explicit formulas here, different sigma notations, different lots of things give us the same answers. That's what's cool about this section here. All right, so how are we going to, well, we're not done. 1, 2, 3, 4, 5, 6. We have to go up to 6 on this one to make it work. So my next question is going to be, how do we make this work if we want to start with k equals 0? Well, it's kind of easy. We just have to modify things slightly. So here we go. I'm going to modify it slightly. So what do we got? Across the top, got a little sigma notation here. Let's start at 0. You know what I'm going to do? I'm going to copy. I'm going to copy my exact formula here, except I'm going to change everything by 1 because this works. So if I want to start it at 0, all I have to do is make each of the k's 1 higher. So let's try that. So 1 over k plus 1. Because now when I plug a 0 in, it'll still give me the 1. Before we had, when we plugged a 1 in, it was 1 over 1. I still want 1 over 1, but here we have a 0 we're plugging in, so I need to add 1 to it because I start one number lower, if that makes sense. Okay, now let's talk about this -1 business. The first term has to be positive. If I plug in a 0 up here, guess what? Anything 0 powers 1, it's going to be positive. Or I can play the same game I played before. I started at 1. If I move the index here, the lower bound, if I move it down to 0, I just have to move the k up 1 so that we start at the same place. Guess what? I can move this up 1. Instead of k plus 1, I can make it k plus 2, but that's redundant because you're going to get the same thing. If you move it up 2, when it's even, it's still going to be even, and when it's odd, it's still going to be odd. So I can just leave it as k. How many places do I have to go? 5. All right, you might have to pause the video and look at this now. Look at it, write it out both ways, and make sure you get the same answer because they both are equivalent. They give you the same series. When I plug in a 0, I get 1 for the first term, and I get positive. When I plug a 1 in, I get 1/2. That's going to be my second term, and I'm going to get negative. So either way will be fine. Now it's your turn. Here's my hint. You do number 11, pause the video. Look at the number. Let's write this. What do we get? This is 3 squared, 3 to the third. Oh, look at that. I'm giving you hints. 2 squared, 2 to the third, 2 to the fourth. What are we going to put here? Let's put that over 1, just so we can do it. All right, pause the video and try number 11 by yourself. Go. Okay, so I'll just come out with my first formula here. What do we have? Sigma k equals 0. So here's what I did. I noticed 2/3, 2/3, 2/3. It's 2/3 to some power. Now, maybe you didn't notice that, and again, maybe you wrote this a different way, but that's what I noticed. The first term has to be positive, so it's going to be -1. You got to deal that -1 trick here, so you have to deal with that. I put a -1 in. I'm going to raise it to the k power, because if I do that and I start at 0, plug a 0 in, turns out to be +1, so my first term will be 2/3 to the 0 power, which is 1, times -1. To the 0 power, which is 1. So 1 times 1 is 1. Let's try the next number. You plug a 1 in, you get 2/3, negative. So it ends up -2/3. All right, plug a 2 in. 2/3 squared, that's 4/9. This will be positive, so you get +4/9. So that works well. So now the only other question is, how can I rewrite this? Just by changing what the index is here. We get k equals 1. We want to start at 1 and go to 5. And as I said, I'm just going to change the values in the formula like I did before. So I get 2/3. I wanted to start it at 0. When my index change, the lower bound changes here, k equals 1. I'm just going to go like this, k minus 1. That's going to start it at 0. And what do I have to do for the -1? Well, times -1 to the, it's going to be off 1 now because when I plug in, if I put a k up here, let's put a k in, then it's going to end up being negative that first term. Well, nobody wants that. We want it to be positive. So you can either do +1 or -1. You got to do one of them. So I'll do +1. Doesn't matter. You can do k minus 1 as well. All right, so final answer here. We have sigma notation in the top. K equals 0 to 4. 2/3 to the k, -1 to the k. Writing it with an index of k equals 1. So k equals 1. We start at 1. We plug it in. We get a 0. That's going to give us a 1 right there. That's going to be -1 squared, so that is going to be positive. We're good to go, and it'll write it out in their equivalent. So look, 2 different ways to do it there. Okay, lastly, this calculator mode here, going to function to sequence. You can hit the mode button, change it from function to sequence, then you hit the y equals button, go in there and put in your sequence, and it'll do the whole thing for you in the table. Go to Google and look it up if you want to learn. You guys are like 21st century kids. Hey, this is Mr. Kelly Baumler. Remember, it's nice to be important, more important to be nice. So